Yes, thank you very much for the organizers for having me. Is it working okay, this sound? Okay.
We don't know, but we'll see on the
So everything that I'm going to talk about is a joint work in progress with Tasos, Moulinos and Azouri. So this is a project that is very much in progress. So any and all result that I'm going to mention is not definitive yet, or any result of our own that I'm going to mention is not definitive yet. But since the time of the conference arrived before we managed to finish the project, it arrives sometimes. I thought that it could still be interesting to talk about what we are trying to do, and this could also be something that could lead to collaboration with some other people in the audience who would like to work on the same thing. So let me now describe what the background to what we're trying to do. So the question arises from a classical question in algebraic geometry, understanding how a family of varieties can degenerate. So let's fix some notation. So except in some very specific cases where I'm going to mention context, I'm going to work throughout over a field of characteristic 0. So K will be a field of characteristic 0. And suppose we have a variety, a smooth K variety. I'll generally write n for its dimension. And we have a map to A1, which, let's say, we will assume that it's flat, proper, and not smooth, but smooth over GM. So this describes for us a family of varieties over the affine line, which is smooth outside 0, but then at 0 the fiber might be singular. So since n is the dimension of the total space, this is, say, flat, dominant, or surjective map. And so the fibers are n-1 dimensional. They are smooth away from 0. And then at 0 we have some degenerate n-1 dimensional variety. And one would like to understand in general what kind of degenerations can happen for a certain geometric type of variety. In what possible ways can it degenerate? So there are many geometric questions which one can ask about variety. Here I'm going to think about the Euler characteristic of the fiber. So how the Euler characteristic of the smooth fibers can change to the Euler characteristic of 0, and if it changes, what controls that change. So what kind of Euler characteristic am I talking about? So if I would have said K being complex numbers, I could say the topological Euler characteristic, but here I want to work over a general field of characteristic 0, so I'm going to work with Euler characteristic of Eladic étale cohomology. So say for for the smooth fibers, say I take some point in GM, I can consider the fiber over that point, and I can consider the Euler characteristic of this fiber. So we're here, let's say, let me fix an algebraic closure. And let me take a point, say, a geometric point. So this thing is the L-adic homology over the algebraic closure. Maybe to be even more clear, let me write x bar for the base change to the algebraic closure. And this Euler characteristic...
There's a -1 to the I.
Yeah, there's a -1 to the I, definitely. Thank you. This Euler characteristic doesn't depend on T, so these, since it's smooth over GM, all these Euler characteristics are the same, so I might as well denote it in a way that doesn't make reference to T. So let's call it chi generic for the generic Euler characteristic. And on the other hand, I can also consider the Euler characteristic of the fiber at 0, which I will call the special fiber because of the analogous situation where we have an infinitesimal family, where it's usually called special. And I can similarly define the spatial the Euler characteristic of the special fiber. And a natural question is, what can be said about this difference? Or describe it in terms of something, notably something that has to do with the singular locus of the spatial fiber. And so when the singular points of x0 are isolated, the situation becomes considerably simpler. And this goes back to classical work of Milnor, who defined a very neat formula for the difference between these Euler characteristics in terms of Milnor number, the Milnor numbers associated to the singular points. So let me recall how this is defined. I have to. Sorry, don't.
You have to turn them around, the long ones.
Neat. Okay, so suppose that we are in the situation of isolated singularity. So suppose we have a finite collection of singular points, P1 to Pn. Then I want to define their Milnor numbers in order to tell you what Milnor's formula. So we can do this formula. Let's assume for simplicity that these points are defined over the base field, even though this is not necessary, but it will just simplify things for me. Then, so we had our function f, and around a particular singularity pi, we can choose local coordinates say x1 to xn. So or local coordinates here in the sense that the completed local ring at x will be the ring of power series, and then I can take my function f that goes to a1, and I can write it locally in these coordinates. So locally at locally at Pi, I have some power series that describes my function f, and I can look at the Jacobian ideal which is so the Jacobian module where I mod out by the ideal generated by the derivatives of f. And because the singularity is isolated, this is going to be something which has finite dimension over k, and this maybe is a bit slightly too low. And the Milnor number at the point Pi is the dimension over k of the Jacobian module. And then Milnor's formula reads that the special Euler characteristic minus the generic Euler characteristic is equal to minus 1 to the power of the dimension sum over these Milnor numbers, these local indices which describe the singularity. Now, so Milnor proved this over C, but one can use similar. I mean, one can adapt the proof to field of characteristic 0. And
Sorry, just a silly question.
Yes.
So does this have anything to do with Moulinos fibers?
With?
Moulinos fibers in nearby cycles?
Yes. The Milnor fiber is how the generic fiber, or the fiber over points that are not 0, looks like in a neighborhood of the singularity. And in the neighborhood of the singularity, the contribution of the singularity to the Euler characteristic is 1. The singularity, near the singularity is contractible. And near the singularity, the Milnor fiber contributes something that is different from 1, and the difference between them is the Milnor number. And that's how Milnor proves it. He works over C, and he has very topological geometric arguments.
Yeah,
Sorry.
Fiber is mu copies of sphere.
Yes.
Dimension n.
Yes.
Joined together at a point, and that's just the Euler characteristic.
Exactly. So a wedge of spheres will contribute, 1 for their H0 plus the Milnor number for the spheres, which is either 1 or minus 1 according to the dimension. The singularity contributes 1, and then the difference is exactly the Milnor number. Now, what happens if the singularities are not isolated? So, for general singularities, so one can use Fulton's localized Chern classes in order to define the thing that needs to replace mu. So Fulton has a different terminology, but a different notation. But let me write this something like this. So here, so this is the vector bundle of one forms on X. X is smooth over K, and to a vector bundle and a section, Fulton defines a localized Chern number that in these configurations of dimension who live in the zeroth Chow class, this is the vanishing locus of the section. So V is vanishing locus of our section. And Fulton already mentions in his book Intersection Theory, he says, this can be generalized using this. He doesn't really prove it, but I think it's, he says more or less how this would be proved, but let me credit it to him for this purpose. And then the statement is that special generic will be minus 1 to the n, and the degree of this localized localized zero cycle, again with the contribution of a sign depending on the dimension of the total space. Okay, so that's very cool, and one can now generalize the question in several directions. One direction, and I'm going to talk about these two directions, but mostly on the second one. The first direction that one can generalize, and which I'm not going to say much about, is that one can consider, instead of a family over A1, one can consider more generally replacing A1 with a base that is the spectrum of a DVR, in which case you can, so instead of A1 here, A1 will be replaced by, say, a power series. It will be the DVR. But thinking in terms of spectrum for DVR, we can replace, either we can generalize the characteristic to a positive characteristic, one direction, or we can have our A1 being replaced with a scheme of non-equicharacteristics, so say something like the periodic integers or something like this. In this case, the generic fiber and the special fiber are varieties living over fields of different characteristics. So I'm not going to say much about this, but I have to say a little bit so that I can say what I want to say after. So this will be spectrum of a DVR, maybe with some niceness. Maybe with some conditions, and I'm going to consider. So X will be a regular scheme. So this replaces the fact that before the total space was smooth over K. X a regular scheme. Let's say F flat and proper. And smooth generic fiber. Okay, so this DVR has a fraction field and a residue field, and can call them a little s in big S, and eta in big S will be the special and generic point. And then we can define more general, we can define same as before. This will be the so this is the special, so small s. And L will be co-prime to residue characteristic. The same, but so let me write this. So these will be the separable closures of the closed and generic point. And one can again ask, what can be said about this? So first of all, if we remain even if we remain in the geometric situation of equicharacteristic, but we just remove the assumption that the characteristic is 0. Already, if we try to, so a priori we can still define everything the same. The formula doesn't hold anymore. There is a correction term that enters in terms of the Swan conductor. So there is some correction term that needs to be added, but one can still ask, okay, what can we say about this? And then in the equicharacteristic case, the same formula remains true. You can define this in the same way. The same formula remains true, only with this one conductor added, and this was proven by Saito. And in the equicharacteristic case, in the non-equicharacteristic case, so if this is like if the DVR is like the p-adic integers, then one a priori, one doesn't immediately know what this is. And Bloch in his work, what he did is that he found a way to generalize this definition of the localized Chern classes to the non-equicharacteristic case.
Sorry, I'm confused. So where does the Euler class lives if you in characteristic P? And because here
I see it's still in Chow group as far as I understand. But in the end, one will take its degree and will get a number. I think this still works the same. So let me write the same thing.
So what is omega 1 here? Because there's some absolute omega 1 because there's a base point.
But so in the equicharacteristic, yeah. Okay, let me go back to the other board. So I'm not going to tell you what it is in non-equicharacteristics, just going to say that. So then Bloch started thinking about this problem. And he found a way to define the analog of this. So one answer is that instead of having the bundle of one forms on the total space and the section, one considers the relative sheaf of one forms. But this still, and so this lives in, let's say it just lives in the special, at least in Chow of the special fiber. So this, under the standing assumption, the locus of the vanishing of df is contained in the special fiber, and so it doesn't matter that much if we take our localized Chern class in Chow of the of the entire special fiber or only in the singular locus, because in the end we are just going to take its degree. We can push it forward also to the... and then he conjectured that this always holds. And so this is called Bloch's conductor formula. So, this is a conjecture. In what situations is it known? So,
can I ask, is this, in the equicharacteristic case, is this degree of this Cn the same as the degree of the local Cn? Is that the same thing?
yes. So, yeah, I mean, yeah, he generalized this construction to the non-equicharacteristic case. So, yeah, in this, as far as I understand, it gives the same number. Okay, so non-case, so, okay, there is as I said, the equicharacteristic case. So let's say Milner Fulton mentions it characteristic 0, and then Sato in positive characteristic. And then for the non-equicharacteristic, so okay, n equal 1 it somehow reduces to a classical statement, to a classical conductor formula for extensions of p-adic fields. So this means that the total space is one-dimensional and the fibers are zero-dimensional. So it's an extension of DVRs. N equal 2 was proved by Bloch himself in the paper where he conjectured this. So this is when it's a family of curves over S. Sato, when the spatial fiber reduced is a normal crossing divisor. And then finally, this was what made me discover this topic, which I didn't know at all. Toën and Vezzosi introduce a categorical approach. So their categorical approach in itself did not produce, just purely in itself, did not produce new cases of Bloch's conductor formula, but in collaboration with their joint work with other people and with some complementary work, it did give new cases. So let me write more names. So here there is a four-author paper which contributes a central part. And then there is a complementary work. I'm just bad with spelling. of names. Of Beraldo Pippi. And this gives some new cases. Proves two new cases, which is isolated singularities and singularities plus a unipotent monodromy. Which kind of combines, so the case of reduced normal crossing is a special case of a unipotent monodromy. So there is unipotent monodromy plus isolated singularities. And another one is that X is a hypersurface so hypersurface is always of codimension 1 inside a smooth scheme plus unipotent monodromy. So it's all inside the domain of unipotent monodromy. And here it's basically it's a condition that makes it a little bit similar to the geometric setting. So in the geometric setting, we have X over A1, but we can also view X as a hypersurface inside X times A1. And if here you can view X, if there is some Y that is smooth over S and you can embed X as a codimension 1 over Y, this magically makes many tools from the geometric setting work also in this setting. So this work, which, I mean, I think the as far as I understand it, I mean, this strategy originates from the idea of Toën and Vezzosi, but realized by collaboration and complementary work of several other researchers, leads to these new cases. So this was one direction in which one could generalize the characteristic zero Bloch's conductor formula. There is another direction that one can generalize, which maybe will be of specifically in the theme of this conference, and that to replace Euler characteristic with the quadratic Euler characteristic. So what will be the quadratic Euler characteristic? So let me again write some names. So in the so now we go back to X to K being again a field of characteristic 0. If we have a smooth and proper variety over K, then the suspension infinity plus of X considered as an object in the stable Motivic category is dualizable. So let me write some names to credit for this. So In several works, different independent works that contribute to this result. And what this means is that one can, since this an object is dualizable in a symmetric monodal category, one can associate to it in a completely abstract categorical fashion an associated Euler characteristic or dimension object or just call it that lives in the endomorphism of the unit, and this by Morel's theorem is the Grothendieck-Witt group that we've already encountered. So the Grothendieck-Witt group is the Grothendieck group that is associated to the monoid of unimodular quadratic forms. So we can think of it as a class of a quadratic form. And since we are in characteristic 0, we can take advantage of resolution of singularities which means that we have always nice smooth compactifications. We can, in fact, remove the properness here. So even if x is smooth, is enough to have x dualizable, so we again have chi of x, and in fact, even if x is not smooth nor proper, one can still associate to it a type of Euler characteristic or an Euler characteristic with compact support. So if P is our structure map and X just is of so just a variety. So it means of finite type, separated, etc.
So in this case, by Euler characteristic, you just mean the trace of identity, right?
It means also a trace of identity.
Okay.
Then this object, the exceptional push forward along the structure map of one is also dualizable, and its Euler characteristic doesn't coincide with this Euler characteristic. It's what is also called Euler characteristic with compact support. But has the advantage of being defined essentially always, where one has that it has the following two properties which are funny together. It differs by if X is smooth of dimension n, then it differs by an nth power of the form -1. So that's the quadratic form. That's the class of the quadratic form with one-dimensional space, and the bilinear form has -1 in its definition. And at the same time, it's also equal to it for smooth and proper. And these two properties seem funny when you put them together. They seem to almost contradict each other, but they don't contradict each other, because what happens is that when X is smooth and proper and of odd dimension, its Euler characteristic is always a hyperbolic class. And so working with the Euler characteristic with compact support, one can try to ask what can be said about the difference between the special and generic fibers. And one immediately comes to a hiccup, and that is that now even if one considers, so we are considering a map to A1 satisfying the same hypothesis as before with over a field of characteristics 0, but now the Euler characteristics of the various fibers over GM, if we take, for example, points defined over the base field and we look at these fibers, we look at their Euler characteristic, this Euler characteristic can change. So we don't a priori have the generic Euler characteristic. The special Euler characteristic we have, but the generic is slightly problematic. So there are several ways that we can try to bypass this. One, we can say, we can ask for the difference between the fiber at 0 and the fiber at 1. The Euler characteristic of the fiber at 0 and fiber at 1, that's well defined. We can also consider some Euler characteristic over GM that would live in GW of GM. So even if it's no longer true maybe that the endomorphism of the unit of the Motivic category over GM is GW, it still maps to GW. There will still be a shadow of this Euler characteristic in GW of GM. There is still some class like that. And then we can, there is also the structure map from GM to spec K. There is also a way to take a class in GW of K and make from it a constant class of GW of GM, and we can compare them in GW of GM. That's another possibility for what we can do. We can also remember this and say, okay, if we are just acting like researchers in the dark and we're just trying to see what might be true or not, we can strict attention to the case where the relative dimension is odd, so that the smooth fibers are smooth and proper odd-dimensional varieties, and so it's hyperbolic all the time, in which case it's constant. So that's three situations which we can just look to see if anything that could be made sense by looking at specific cases. So in either of these three cases, we have the left-hand side, but we need also the right-hand side. So what about the relative Chang class? So for the right-hand side, there is a local Euler class. That one can consider. So this, if I understand correctly, first appeared in sorry about this. Yes. In two papers, and one can put this on the other side, this local Euler class, and see what happens. And in the paper of Levine, Simon, and Srinivas, they checked it in some explicit examples, and they saw that sadly it just seems to not be true. And they offer a modified formula with a correction term, both a multiplicative and an additive correction term. So there is something that multiplies the Euler class, and there is something that is added to it. And that was the point in which we entered the project, and our idea was to ask, can we do a categorical approach in the quadratic case? And for the very beginning of this approach, the only thing that I would like to tell you is that at least, so two observations that we had. One is that even though this seems to not be true in the examples that that I mentioned before, it does seem that in cases of so the authors I just mentioned, they looked at cases. So these are cases with isolated singularities. Inside isolated singularities, there is the particular case of quadratic isolated singularities. And a quadratic isolated singularity can be split or not. There is a quadratic extension associated to it, which can be trivial or not. And if one looks in the cases where this quadratic singularity is split, then in fact, the original formula, this minus this equals this, actually holds without any correction terms. And we looked, so at first we thought this was just a coincidence, then we looked in what happens for a general family of curves which where the degeneration has only split quadratic singularities. So if you think of a family of curves, and then there is the special fiber or something like this, and you assume that the degeneration has is a normal crossing divisor, but also the splittest possible. So everything is defined, all the components are defined over the base field, and all the intersection points of the components are defined over the base field. Again, it's a family of curves. If you look at that case, then actually you will see that the quadratic enhancement is actually implied by the non-quadratic one. So it still holds. So at that point, we started thinking that maybe there is a chance that even though it's not true in general, it is true in a case which is sufficiently split. So the conjecture that I kind of want to, that I imagine at the moment is that there is a chance that this thing is true for, that the analog of the formula is true for normal crossing, when the special fiber is a normal crossing divisor, which is fully split. So careful conjecture the quadratic formula holds when x0 is a split normal crossing. This, from checking specific cases, this looks true. And the second thing that I want to tell you, because in any case I'm at the end of time, is that the reason why I have the possibility to check cases which are beyond the isolated singularities is because we know how to define this when the singularities are not isolated. So as far as I'm not an expert in this, but I didn't find in the literature a definition of this when the zeros of the section are not. You have a definition? Yeah, sure. Okay, but if you want a definition that is in the spirit of the Toën and Vezzosi approach, and I'll just say it in words because I'm out of time. So, what is observed in the non-quadratic case, in the classical case, and in the characteristic zero case, is that this number, this local Chern class, is also the Euler characteristic of the singularity category. So the singularity category is something that is itself is a smooth and proper object when you consider it over the correct base. What we can do is we can take these approach, these definitions, and consider the singularity category as a type of object whose Euler characteristic will not just give, say, a complex with an Euler characteristic, but will give a complex with a quadratic form, which will have a quadratic Euler characteristic. And for this, one needs to refine the singularity category to something which has an extra structure, the structure of a Poincaré category. So this takes into account the fact that on the singularity category, there is a duality, which comes from Grothendieck duality. And if one does all these computations, one arrives at, say a theorem. I'm going to write on the board. So the singularity category or infinity category is dualizable over a certain base, which is I will say in a minute what it is, as a category with duality. So not only as a category, but also when one considers the duality that is associated to Grothendieck duality on it. It's Euler characteristic, so this would be something that lives so it's not will not be in Grothendieck width of the field, but in Grothendieck width of this base. Is compatible, let's say, with this local let's just say it's compatible. So what do I mean by this? I mean that in the situations where I could find the definition of this, which is the situation of isolated singularities, then one gets the same answer. But this gives an answer that looks well behaved in general, and so I will be very interested to compare with the other definition. And this enabled us to check more general cases of normal crossings, and so far I didn't find a counterexample. So what I'm thinking is that there is some correction term that needs to be added to that somehow measures the non-splitness of a quadratic singularity, or no, so something like this that will explain why in the split case it works without any correction term, and this would maybe say what the correction term needs to be in general, but this I don't know yet. But anyway, thank you for listening. And
other questions? Mark.
So you mentioned the split and non-split phenomena for isolated quadratic singularity.
Yes.
Is that just the homogeneous singularity, and you look at the associated quadratic is split or not split? Is that what that is, or what is it?
If you have a quadratic form, if your singularity looks like this, and n is even, then it's minus 1 to the n times the discriminant of f.
No, I mean, but the condition on the,
This needs to...
the discriminant needs to be minus 1.
Yes. So if you think, okay, it needs to be the same. It needs to be the same discriminant as a hyperbolic form of this dimension.
But that's just saying the middle dimensional linear spaces are the two different families are defined over your field.
Yes. Exactly.
Oh, okay. But isn't that the same thing? Okay.
I mean, there is some. So there is a quadratic extension that controls these two families, and it's not the discriminant, but minus 1 and the times the discriminant.
Great. Thanks.
Tom?
So you say that there isn't an obvious generic Euler characteristic anymore.
Yeah, there isn't an obvious generic. What I'm hoping in that will save this is actually that it looks like the Grothendieck-Witt group of, so this algebra is not an ordinary ring, it's a DJ ring, and beta sits in degree minus 2. So it's a little bit hard to immediately get intuition on what the Grothendieck-Witt of this should be, but from various manipulations suggest that the Grothendieck-Witt of this and the Grothendieck-Witt of GM are actually not that different from each other. They both sit in somehow in similar exact sequences relating them to GW of K. And so one might, and also it looking at computing this explicitly also shows that in these cases where the total space is even and the relative dimension is odd, so the generic fiber Euler characteristic is constantly hyperbolic. In those cases, this categorical Euler characteristic is also constant. It comes from GW of K. So they are both constant and non-constant at the same time, and they both live in groups which seem kind of similar. So I'm even hoping that in the best of all possible worlds, these groups are somehow maybe isomorphic in some situations, and so you can just compare these three things: the special Euler characteristic, the generic one that is in GW of GM, and the singularity one which is in GW of this. You can somehow put them all in the same group and do this plus this minus this and get 0. But so far I don't know how to do that.
But my question was supposed to be a bit more naive. Like you say, you take, for example, the Euler characteristic at 1, but you
Yes.
know it's sometimes different from the Euler characteristic at 2, or?
Yes. So definitely they can construct easily examples where the Euler characteristic at 1 and the Euler characteristic at 2 are not the same class in GW.
But it's special because you're looking at a family which is proper over A1. And so it's really smooth and proper over the GM. So
Yes.
It's really, and then this thing at 1 is the specialization.
Yes. So looking at 1 does give something interesting. So the Euler characteristic in 1 and in 2 can be different, but the way that, I mean, since it's smooth and proper over GM, I mean, you do have a class in GW GM, and a class in GW GM, I mean, we know how this group looks like. So there are very specific ways in which this Euler characteristic can vary along GM. And so for this reason, taking the fiber at 1 is not forgetting that much information. And one can somehow hope that there would be an analog homomorphism from GW of this to GW of K, which is analogous to evaluating at 1, and then being able to at least compare everything in GW of K. But what happens in the non-quadratic setting is that basically K, GW, and this all have the same K0, which is Z. And so they become numbers that can be compared. But in the quadratic, you have 3 different GW groups. And yeah, so either you somehow identify in some way GW of this and GW of GM, or find a way to project everything to GW of K.
Relatively, if you're in mixed characteristic, do you have any guess how you might relate the different characteristics?
So in the mixed characteristic, the categorical approach is much more difficult. So that's the main contribution of Toën and Vezzosi. And there is somehow an extra complication is that what replaces this coefficient ring is something that is no longer a commutative DG ring or an infinity ring, but an E2 ring. So something that is a bit commutative, but not completely commutative. This has a devastating result that the derived category of this is no longer symmetric monoidal, but only monoidal. And so actually, there isn't a priori an immediate categorical Euler characteristic. So Toën and Vezzosi, they define something else, a more elaborate type of categorical Euler characteristic that lives in, then it would live in K, or I guess GW in our case, not of this ring, but in its Hochschild homology over S. And that group is, so if this group is since this is not an ordinary ring, this is maybe a bit less immediate to handle. It becomes much less accessible when you replace this with its Hochschild homology. And there is hope to do that, but it seems reasonable to first understand what happens in the equicharacteristic zero case, where at least all these complications like E2 instead of infinity and all these complications don't arise, and just handle the quadratic complications and only then try to think about the general case.
So just a naive question. I mean, by categorical, what do you mean by?
Infinity category.
No. It seems to me that here the picture is somehow. Somehow you just take care of some linear structure instead of symmetric monodal structure. Is that correct?
What do you mean?
Just like the singular category, you don't take care of any sort of symmetric monodal structure.
On symmetric monodal structure on the singularity category?
Your formalism doesn't.
I mean, you would need it would need to live in order to have the Euler characteristic. It would need to live in a symmetric monoidal infinity category. So.
Yes, but it is this category. This category lives in a category of categories.
Yes, it lives in some category of categories, which is some category of K beta linear categories.
Yeah, but anyway, your input doesn't has a symmetric monodal structure.
It doesn't need to. It needs to be an object in some symmetric monoidal category. So it lives in some big category of categories, which are also linear over some base. They have a tensor product of tensoring them over the base, and that's symmetric monoidal, at least when this is a commutative ring. But that part is the part that becomes more difficult when you go to non-equicharacteristic, and then it becomes this is replaced by some E2 ring. It becomes only a monoidal category, and then it's harder to define an Euler characteristic.